Welcome back to Logic, Language and Information. In this lesson, we'll continue our introduction to digital systems and how they are grounded in logic. Today, we'll get some hands-on experience with the basic logic gates, and, or, and not gates, and see the build-up and design of combinational digital systems using circuit diagrams. We'll also see how circuit diagrams are used together with logic formulas and truth tables to design and analyse such systems. So let's begin. In this lesson, we'll look inside the black box of combinational digital systems. We'll get to see the familiar propositional connectives of and, or, and not in a different light. Instead of being the glue that connects propositions, the logic gates of digital systems are elementary systems in their own right, defining an input-output relationship on digital signals. Logic gates are the basic building blocks out of which complex combinational digital systems are constructed. First, the AND gate. In its simplest form, an AND gate is a two-input, one-output system such that the output is 1 if and only if both the inputs are 1. We assume you know the truth table for AND. The standard symbol for an AND gate is characterised by the round output end and the straight input side. In the notation of Boolean algebra, standard in the digital systems literature, A and B is written in product form as AB. Equivalently, the output is 0 if and only if one or more of the inputs is 0. AND gates with more than two inputs behave analogously. The output is 1 if and only if all the inputs are 1, whether it be 3 inputs or 4 inputs. Equivalently, the output is 0 if and only if one or more of the inputs is 0. Next, the OR gate. Starting with its simplest form, an OR gate is a two-input, one-output system such that the output is 1 if and only if one or more of the inputs is 1. Again, we assume you know the truth table. The standard symbol for an OR gate is characterised by the pointy output end and the curved input side. In Boolean algebra notation, A or B is written A plus B because OR is the Boolean sum operation. Equivalently, the output is 0 if and only if both of the inputs are 0. OR gates with more than two inputs behave analogously. The output is 1 if and only if at least one of the inputs is 1, whether it be 3 inputs or 4 inputs or more inputs. Even simpler among the basic gates is the NOT gate or inverter system. It is a one-input, one-output system with the property that the output is always the Boolean negation of the input. Input 1 results in output 0 and input 0 results in output 1. The standard symbol for a NOT gate is a triangle followed by the inversion bubble. There are two other logic gates that can be used as basic building blocks. The NOR gate is a two-input, one-output system, equivalent to taking an OR gate followed by a NOT gate. The output is 1 if and only if both of the inputs are 0. The standard symbol for a NOR gate is an OR gate followed by an inversion bubble to indicate negation. The dual to NOR is a NAND gate. It is a two-input, one-output system in its simplest form, equivalent to taking an AND gate followed by a NOT gate. The output is 1 if and only if one or more of the inputs is 0. The standard symbol for a NAND gate is an AND gate followed by an inversion bubble, again to indicate negation. The NAND and NOR gates are quite well known in logic under different names. The Sheffer stroke for NAND, dating from 1913, and the older Peirce arrow for NOR, going back to 1881. As a logic connective, each has the property that all of the classical propositional connectives, and, or, not, implies, and if and only if, can be rewritten with a logically equivalent formula containing only nands, or only nors. For example, not A is equivalent to A NAND A or B is equivalent to A NAND A, NAND, B NAND B, and A and B is equivalent to A NAND B, NAND with A NAND B. As a consequence, any combinational digital system can be built using only NAND gates, or alternatively using only NOR gates. One final combinational system is the exclusive OR, written XOR. It is a 2-input, 1-output system with the output 1 if and only if exactly one of the inputs is 1. Or equivalently, the two inputs have opposite bit values. Clearly, we could have built an XOR gate out of AND, OR and NOT. To see this, we can equivalently write this as Z if and only if P and not Q, or not P and Q. XOR gates are useful because they behave essentially the same as binary addition, the plus operation numerically on binary numbers. We have now introduced the basic systems, the logic gates. Next, we need to set out some rules for putting together these basic building blocks to create bigger, more complex systems. First, we'll clearly identify input and output signal wires with labels, and we use labels for atomic propositions, which are lowercase letters. Next, the basic building blocks are the logic gates, so AND, OR and NOT, or just NAND alone, or just NOR alone. The basic gates are connected together using signal wires. The output of one gate can be connected by wire to the input of another gate. A signal wire can be split or branched in a forwards direction to allow the same signal to be fed forward to two or more other gates, with the branching indicated by a bold dot. But in the construction of combinational digital systems, we do not yet allow feedback loops. This sort of feedback is a crucial feature of sequential digital systems, will be introduced in the successor course, Logic, Language and Information 2. From a propositional logic formula expressing an output in terms of the inputs, we now have a recipe to construct a circuit diagram starting from atoms for input signals and building up with the connectives using logic gates. The two-dimensional layout of a circuit diagram forms a template for physically building a digital circuit. The signal lines show where to put physical wires, and the logic gates are typically implemented using analog transistor devices. Regardless of how logic gates are physically implemented, space matters. We want and need to design circuits that have a minimal number of gates and minimal sized gates in their number of inputs. This will be the content of the last lesson on digital systems. The basic gates are all one-output systems, but when composed together according to the circuit diagram construction rules, it is easy to create systems with multiple outputs. Using feed-forward branching, any component can have its output branched and sent via other gates to separate outputs. For this lesson, we're interested in developing the skill of reading circuit diagrams for combinational systems in order to extract a logic formula for each output, expressing it in terms of the inputs. A systematic way of doing this is by labelling each of the intermediate signal wires with appropriate logic formulas in order to capture the build-up to the output. Let's look at an example with three inputs P, Q and R and one output Z. Starting on the left-hand side for the inputs and working towards the right-hand side for the output, we have the input signals P and R both branched and negated, while the middle input Q is fed in without negation. So we get not P and not R as the outputs of the respective NOT gates. Then coming out of the AND gates, we have from the top P and R, not P and Q and R, and finally Q and not R for the lower AND gate. These three conjunctions are fed into the final OR gate to give a disjunction of conjunctions that is equivalent to, or truth functionally the same as, the output Z. By assigning some bit values to the input signals P, Q and R, we can see them propagate through the circuit using the intermediate signal formulas to end up with the final bit value for Z. Here, PQR input 0, 1, 1 results in Z output 1, while PQR input 0, 0, 1 results in Z output 0. Another example, PQR input 1, 1, 1 results in Z output 1. And a further, PQR input 0, 1, 0 results in Z output 1. Now, it's your turn to try an exercise. Consider the following combinational circuit with 4 inputs, P, Q, S and T, and 1 output Z. Your task is to read off or extract a logic formula for the output to express it in terms of the inputs. Which of these propositional logic formulas correctly express the dependence of Z on the inputs P, Q, S and T in the previous circuit? Notice that each of the options have the right shape, a size 3 disjunction of conjunctions, where the conjunctions are of size 3, 2 and 3 respectively. Now you have a go. Printing out a paper copy might be helpful so you can label the intermediate signal wires. That's a good way to avoid losing a negation symbol. So how did you go? The only correct answer here is C. The top AND gate gives not P and S and T, the middle AND gate gives not Q and S, and the bottom AND gate gives Q and not S and T. If you have any more questions or comments, first take a look at the course notes and then head into the discussion boards, and I'll check in on the discussion there. This brings us to the end of this lesson on logic gates and logic circuits. In the next lesson, we'll examine the different representations of combinational digital systems, functional descriptions, truth tables, logic formulas, and logic circuit diagrams, and how to transform from one representation to another. So see you next time.